Hi, everyone. My name is Edward. Thank you for coming. It's the end of the conference, almost. It's the evening, a little tired, maybe. What are we going to talk today about is playing C++ on nightmare difficulty. It's going to be about the journey we had at Quasar over the last 10 years, a little bit more than that. And you'll see what I mean by nightmare difficulty. It's a reference, of course, to the Doom game. Initially, I thought I would do a Doom theme, and then I thought about copyright infringement, said, well, let's not, and keep it very simple. So the presentation has 3 parts. The first part is just give you, like, as short as possible to give you the context of what we do. Why we are building what we do, what kind of software it is, the constraints, so that you understand. Then the middle of it is going to be a series of puzzles. All of them are bugs we had in the product, every single one of them. None of them are really hard because what's difficult is to find the bug. Once you have isolated the code, it's pretty easy. What for me would be awesome is like if there's only one person here that realizes, look at this and says, wait a minute, I need to check something. And you come home and you check your code and you fix a bug thanks to this, that would be awesome. And then the third part is really going to be about how we manage the difficulty, what we do, some tips, and don't hesitate to ask questions at any point. That's the perks of coming here, because you get something interactive. And here we go. For the puzzles, you see they're very simple. I will not give you no hints, and then as we move further in the presentation, if you're stuck, I think you will solve all of them. But if you're stuck, I'll give you hints. There, really, don't worry about it. Nothing is easy, and there is no grades. So what do we do? So Quasar is a huge big data AI platform. Insert every keyword you want. Imagine if you were to build an infinite spreadsheet. You wanted to have your users add constantly rows to your spreadsheet and also ask questions to a spreadsheet. And the spreadsheet would be used to do forecasting. For example, forecasting that is predictive maintenance, cybersecurity, finance, which is where the company started. We also have customer and research, like you have very, very complex simulations that generate a lot of data. You want to capture everything and be able to replay everything. That's what we do. We have 10,000 deployments, exabytes of data processed. It's a little bit of marketing. But what I mean is the software is pretty mature now. It's been running production for a while. So we have the Scott issue to be able to talk about some of the issues regarding C++. So what about the constraints? So I told you what we have to build. Now, what are the constraints? The users we have, typically, they want to have no limit in terms of ingestions, and some of them is like terabytes of data per day, billions of rows per second, spikes, everything horrible you can imagine. You have to compress the data because nobody wants to give all their money to AWS. So you have to compress the data as fast as possible. And then you have to answer questions. Hey, do you remember the data stored 2 years ago? Can you find me the byte I need? And do that pretty fast while continuing to ingest the data. And then on top of that, you have the complexity to give SQL interfaces, all the interface you have to build. And you need to do that using as little resources as possible. And it's not really about just performance. Performance is great, but it's the less resources you use, the more affordable the project is. And if you tell your customer you can store a petabyte of data on disk, it's going to be only 100 terabytes. So the cost of the project is much lower. And that's what really matters. Then where does the software need to run? So we use, I didn't use the marketing keyword of edge, but basically it needs to run in small devices. Also needs to run in the cloud. What does running in the cloud mean? It means you need to handle the network is completely random, it's not reliable. You should never assume it's random, but it's not the same as you work on the software that is running in data center where you can master everything, whereas compared to the cloud where anything can happen anytime. And the operating system we support Linux, usually for the server side, Windows, because that's what people use on the desktop. We also have Mac, and we added FreeBSD for extra difficulty. So that's what we mean by C++ in nightmare mode. Not only you have to support multiple platforms, so multiple compilers, multiple operating systems, multiple libraries, multiple implementation of the STL. And you have the software to run fast, be memory efficient, and obviously be reliable. So it's not great. Then why C++? So the first lines of code ever were written in 2009. Back then, the choice for C++ could have been like, why read C++? At that time, it's when you had C++ OX, 11 was not even released yet. And the reason why we picked C++ is control, performance. But there's also the fact you have a large ecosystem of libraries, which means that when you run into a problem, you are pretty certain there's going to be one or two libraries with high quality implementations available. You're also going to have very mature tool chains and everything. And the language back then it started to be actively supported again. It was no longer the 03 that was like feeling like being left alone to die. You started to have lambdas. So the first version ever of Quasar was compiled with GCC 4.6 with the experimental lambda implementation. Yeah. And the reason is when I started the project, so basically almost started from scratch. And that's, I think, the reason why you should pick a language is because it was the language I knew the best. And so why waste time learning a new tool? And I personally like the STL, and also think for hiring, it's a good selection of people to hire. So then a little stab at, oh yeah, but what about using a different language? The complexity, we like to complain about C++, especially if you use it a lot, but a lot of the complexity of C++ is because the problem you're trying to solve is actually complex. And it's not always possible to make it easy. Hard problems don't always have simple solutions. And the goal right there was to solve the problem I described is not necessarily to be advancing the nature of programming languages. And as after 10 years, more than 10 years, I think I'm very happy with the pick of C++. And especially the direction the language has taken in the last year is really awesome. Just a slide to complain about C++, because why not? Compilation times, especially we have a tendency to do a lot of header stuff, metaprogramming, so compilation time can get crazy. You see we have ways around it, but it's still problematic. Package management is annoying. At the end, I'll show you how we manage all the third-party libraries that have to compile everywhere. It's pretty painful when you need to have your library work on ARM, 32 bits, and also Intel, and have the right optimization selected. And personally, the thing I hate the most is compilation errors, where you're being assaulted with a billion rows of messages just because you forgot an include. And Clang made things better, but that's just the thing that personally I hate the most. Okay, is that enough context for everyone? That part is supposed to be the fastest. So now we're going to get into our little puzzles. And I'm just going to show that to you, ask you questions. You can engage however you want. I think most of them are pretty easy, but all of them, every single one of them, production issues, or sometimes you got it before. So question, is this, assuming you have multiple thread calling this, do you think it's thread safe?
Absolutely.
Yes. Right, it is. Why is it not thread safe?
So you can, like, it would work on Intel, but it's not portable.
Even in Intel, it doesn't work.
It doesn't?
I'll show you why, but I mean, it could work if you're lucky.
The guy before you, he said it would work.
So the thing is, if you're lucky, and exactly like you said, if you're like, let's say, just testing on your Windows desktop or Linux desktop, AMD 64, Intel, you might never, ever run into any issue. You might be lucky. But the compiler could do this. And that is not thread safe. So basically what happens is you could load, you have two threads. Let me try this feature. Oh yeah, it works. So here, let's say you have two threads, they're both loading V into a register, they both increase the value, and then store it back, you lost an increment. So even in Intel, you could lose increments. So again, if you could just have a muscle memory like, oh no, in C++11, if I want to do something atomic, I need to use atomic, right? C++11, pretty standard. This is what we want to do. So this is correct. There's no trap. And we are using the memory order relaxed, doing our little increment. Everything is fine. You do your little check in case some implementation of a library decides to use a mutex and you want to be sure that you're completely lock-free. I'm not even sure there's any implementation that has mutexes for integers and atomic, but you could do stud atomic, any variable in theory could work, just so you know. So memory order relaxed is great if you're just, for example, this is like statistics and you want to increase the values. You don't really care about the order. Where you have to be a little bit careful, which is another bug we had in the product. So memory order relaxed, basically, it just says, yes, a guarantee that all your threads, nobody's going to lose a value. But if the order of operation matters to you, then you can run into this kind of issue. So if, for example, you're using your atomic as a fence and you're using the wrong memory order, then this could be incorrect. You need to make sure that it's at least released. But again, some platforms are more forgiving than others because in Intel, as far as I know, it's atomics are pretty forgiving. So far, so good. This one was easy. So I wanted to rate the puzzles. Then I realized, some of the stuff I think it's easy is probably hard, and some of the things is, it's really hard. It's like, nah, it's easy. This one. SIGBUS, sometimes. When the moon is in the right position.
Alignment problem?
Yes.
So, alignment problem?
Yes.
Okay. But is this, again, on some architectures?
Yeah, and sometimes. So
if the variable is you're out of luck.
Yeah, because like it's 32-bit, so it's 4 bytes alignment. And it's taken from deserialization code. And
on Intel, this would work.
Yes, all the time.
Yeah.
And shouldn't that be fairly easy to debug though? Because you get SIGBUS, it tells you the address it tried to access.
Yes.
Say.
Yes, it's pretty easy when it happens, but it needs to happen.
Well, if it's not happening,
Yeah.
then you're lucky in another direction.
If it's that the problem we had and we didn't catch it is because it was in some part where almost always the memory was aligned to 32 bits. We started to have the problem. We had random crashes. We were porting to ARM. So we initially started the product on Intel. We ported to ARM, and sometimes it was crashing, but it was like rare. And so you had to catch it. And once you catch it, it's very easy. So SIGBUS is the hint because SIGBUS compared to segfault means the memory hardware cannot do what you ask. Doesn't mean the memory is invalid. So yeah, some platforms have very strict memory alignment requirements. So if you're storing a 32-bit integer, your memory needs to be aligned on 32-bit, etc. And again, this is like this code is not necessarily wrong. It's like just, needs to be aligned. That's the code that is doing the right thing.
Can you use bitcast also? Bitcast?
Yeah, probably.
I don't think the cast works with this particular case.
No, it doesn't. Yeah, because you have the same behavior, just reinterpreting the same memory address.
It's not a cast problem. It's basically the hardware will just fault on you because you're trying to write 32 bits. Doesn't matter wherever you cast it. And memcopy will actually be pretty efficient because it's like if it's already aligned, fine. If it's not aligned, we copy byte per byte. As far as I know, that's the way to do it proper. But if you guys know something better, I'll be very happy to go home with.
Bitcast actually one possible implementation is a memcopy.
Okay.
They will look at simple reference.
Okay.
Yeah, this is like a case study. Bitcast was added to C++ 20 years.
So bitcast is what version of C++ is that?
C++ 20.
Okay, so it's pretty recent.
Yeah.
So bitcast is doing memory copy.
Yeah, it's actually a function, bit underscore cast.
Oh, it's like a static cast. There is a bitcast.
Yeah.
But it does memory
No,
copy.
it's not a static cast. Bitcast is totally separate. So it actually insert this doesn't.
Yeah, but it's a type of C++ cast.
it's not a.
It's not a library.
Ah,
It's
okay.
not a different function.
Okay.
So yeah, I have to. So here, that's actually a little segue. This is like deep into serialization code, and I think this code has been left untouched for 6 years. And so if you say, hey, what about you use the latest thing? It's like, do I want to touch the code that is called by every single function ever? Or I want to keep it the way it is? Even with the confidence we have with all the tests and everything, there's always this trade-off, and I'll talk about it at the end. And we always try to modernize the code. Like as we upgrade compilers, we currently at C++ 20, we always try to modernize the code, but not to an extent where, we're going to look at every single part of the code and change everything to the latest thing. There's always a trade-off. But I'll definitely look into it because I don't think memcopy is.
Bitcast does not work here because it takes the wrong kind of input.
Okay.
It doesn't take a pointer, it takes something like a float.
So I know what, so it's like if you want to cast a float into a zone of memory, what? Okay, so are you telling me there is no other way to do this?
This is the way I've always
This is the
used
right
it.
way to do it.
Huh?
This is the right way to do it. Yeah, because the void server there, right? That can be a 64-bit or something, right? So bitcast ensures that you need to have the size will be the same. So
Okay.
at least we have to do that.
Okay.
Yeah, I think this is the best way.
Okay, well, I don't think it's worth adding something in the standard for this, to be honest. Okay, this one is very easy. Maybe. Why does it crash?
With referencing
Yeah.
a pointer.
So, of course, we don't write what happened in real life is like you had something like this. Pointer was not null, it was invalid. And you had an API, low-level API that only takes raw pointers. And at some point, you had to feed that into an API that uses references. So, of course, you should never mix references and pointers, but in real life, you are doing this. This one is very easy to catch. This one is a little bit more nasty. So first of all, it's not guaranteed it's going to crash because the compiler could do something where it actually works. Here, this one is very nasty. So assume this doesn't crash for some reason, or it works, or you're doing something with the pointer, you're touching the pointer, you do something. And this will never be printed. For example, let's say you have some macros. I think we talked about it. And you have some macros that do some assertion, and it never is called in release. You have never, in debug, it works, in release doesn't work.
Undefined behavior.
Yeah, it's an undefined behavior. This one, I didn't find this bug, but I'll tell you after what we did when we found it. And it's very nasty. So basically, if you're a language lawyer, you open your book of C++ and it says, oh, you touched the pointer. So I'm allowed to remove this check because I'm going to assume that your pointer is not null.
Oh, I
Yep.
didn't know that.
Yep. Well, we didn't either.
I didn't even talk on the first day, but
Yeah.
you may want to check out.
I didn't know it's funny. We're obviously not the only one who run into this, but it's very nasty because you're like, I wrote this, what are you doing? So there is a flag for GCC to tell him to not do that. So you have to check there is no performance impact for you. But it's super nasty because imagine that you have your assertions or everything and the code is just not implemented. It's an optimization. So technically, this is not correct, right? But it's like really like no shoot, just jump. So the first one is easy to catch. In real life, the problems can be harder to identify because it's going to be hidden layers of different APIs, and you realize there is a reference that is invalid because it comes from a pointer. So there are classes you can use to make sure that your pointers are always sanitized. The second one is, the compiler can just remove the.
You also have the UB sanitizer.
Yes, it should catch it. It should. I talk about the sanitizers later. So solution is like, don't write bugs. It's not great. So in GCC Clang, you can use this to make sure that it never does this optimization, which we put in production. Because you cannot rely on the fact that the software engineers are going to be extra careful about everything. This one, so assume that it's an asynchronous problem, and what happens is the retry doesn't work. Never retry. So it's nasty because it's on a retry. So in production, you have the issue that the retry doesn't seem to work, but it's not really obvious. The retry doesn't work. And you'll assume that your client is correct, the socket is correct. If you don't know ASIO, so basically this is the callback that is going to be called when the AO call returns. When you see it, it's very obvious. It's not advanced C++, it's just pure logic.
When is the capture happening for the retry?
Yes. Which client is in there? So here is like the retry lambda is here. So here you capture the share pointer. So it's this one. Here you close it and you create a new one. But the retry lambda never has a new one. It's working on the old one, which is closed. But no access violation. The client is a normal state object because it's a share pointer. So you debug, you put a breakpoint here, just I don't understand. Then you realize, hey, the client is closed already. What's going on? You step into this and you realize it says, well, it's already closed, nothing to do. Then you realize, wait a minute, so you could be, the naming is not the best, but it's not really obvious. So you could say, oh, don't do asynchronous CIO, but honestly, if you are serious about performance, you have no way around it. You need to use it. And personally, I think share pointer is a great way to maintain the lifetime of something when you have those callbacks, because you don't, especially at shutdown, otherwise you can have a problem at shutdowns. The problem is asynchronous code is it's much harder to debug. And because for the human brain, it's like, okay, I have to basically think in parallel. And there is no real easy way to make your asynchronous code more reliable. I wish I had like a simple formula. It's more testing, careful development, and a little bit of rigor. Thread sanitizer, personally, I don't think it never ever caught anything really cool. Yeah.
Actually, I'm not sure about asynchronous, but non-blocking I/O becomes much simpler if you're using microthreading.
Oh yeah, you can use non-blocking I/O as well. Yeah.
And then with microthreading, your code is simple.
Yeah. You can not just for ASIO, you can also use fibers. So coroutines, it also makes reading easier. Matter of taste. What we like about so first of all, some of the asynchronous logic is like almost a couple of years old, so we're not going to rechange the whole architecture. But for network, we're pretty happy with asynchronous I/O in terms of performance. And so we're not going to rewrite everything. If you want to see what the one correct way of doing it is, you can just declare the retry lambda here and capture the correct client. What I don't like about ASIO in general or async is like it has tendency to do a little bit of Russian dolls, so where you have the lambdas inside the lambdas and all of that. So it's a little bit annoying, but yeah, we got really good performance with asynchronous call, and we use the version of Azure that is in Boost. We'll talk later at the end of later in the presentation what we do in terms of libraries, how we manage all of that. So far, so good. Any questions? So I don't think this code is going to win a beauty contest. Just I'm aware of this. Okay, so this one. So what it does is, so this is like a 128-bit register, and this returns the first float in it. And what's wrong with that?
Is the alignment incorrect? Indepth.
No, actually, there's nothing wrong with it. But the problem is the compilers decide, yeah, I don't care about I don't care about it.
So the floating points are kept in as in the register in the line 0.
Yeah.
So this just compiles to nothing.
Yeah,
But there is no problem here.
there's no problem.
Yeah, but you didn't expect that.
Yes, there's no problem. It's correct. Your program is correct. So because what I really tried is to reproduce a problem we had where we had a complex optimized serialization routine written in single instruction multiple data, and there was nothing left. The compiler looked at it. So something we learned is the compiler is not obligated to honor your intersex. He can do whatever he wants.
I know for sure that I achieved the same behavior as you. I achieved it stores SS store F32 to a memory location, and when you look the compiler output, there was no memory. It was just nothing.
Yeah. And so here in our case, and I could not reproduce it in something simple. It was a pretty advanced serialization code. And the compiler looked at it and says, oh, no, I'm going to do something else entirely. So you could say, well, I don't care. At the end of the day, I just want my code to be efficient. But the problem is, yeah, you actually care because let's say you really think you can do something better than the compiler and you want to be able to iterate and optimize. And so what happened is the developer was keeping iterating and says, I understand I have 0 performance difference with all my implementations. And so at some point he decided to look into the assembly and realized that, well, it's just, there is no, and so we moved the code to an assembly file. And then in that case, well, there's no optimization phase and then you're good.
So I don't understand why you want to do this actually. Like, isn't it just better to have no code? That's just faster, right?
No, I want my function. No, because at the end we managed to do better.
Better than nothing?
No, better than the compiler. What really happened is, so it's kind of variadic encoding of an integer or multiple integers for compression. And the compiler looked at the code and removed all this single instruction, multiple data instruction, and did something using regular instruction because it was faster than the initial implementation. But we knew we could do better through vectorization, but we wanted to iterate, to benchmark and profile. But you cannot iterate and profile if the compiler never optimizes what you want. And sometimes it will, like it no longer recognize the pattern, and so the performance drops, for example, then it goes up and you don't understand what's going on.
What about the -0?
About, sorry, I didn't hear.
-0.
Yeah, probably works. I guess there's some optimization level where you're basically saying disable optimization for the file. Maybe it works.
Yeah, with those 0 it will compile as you would expect.
You can also do that. But then you have to, like, if, for example, if you use CMake, you have to, for your specific file, you have to add specific compiler option, and then you're back in the nightmare that you support 4 different we support 3 different compilers, 4 different platforms. So you try to.
No, but you do the iterations.
Yeah.
With without optimization.
Yeah.
And then when you get something that works, the compiler is not supposed to optimize it away.
Maybe, if you're lucky. It's a good point. You can also, another approach, if you don't want to put it in an assembly file, you can temporarily disable optimization or put it at 0. See what? Yeah, sure.
There might be some other approach also where you can actually specifically take a block and say that it won't optimize over here using that was.
Do you have Pragma to do that?
I think there are some.
Yeah, probably, yeah. Yeah. Regardless, what we've realized is when your optimized function exceeds a certain level of complexity in terms of amount of intersecs, it's better to put in an assembly file because then you control everything, including the registers. Like the compiler is not going to add extra instruction in between two calls. Even though the optimization phase gives a pretty good result, if like it's a very critical function and you want it to be like super optimized, if you want to be a control freak to the max. Okay. Any other question regarding to? Here, imagine there's a client, you're capturing your time since epoch, you send it to the network, to the server on the other one, and then it decodes, and then you don't have the right values. But the integer is correct. Like there is no serialization error. Integer correct is like just the server and the client disagrees on the time that this represents.
Obviously, different epochs.
You sure?
Or different
Standard
clocks.
are you using?
Yeah. So it's actually, this works in C++20. This will not work before. And personally, this is a bug I did because this is where you really have to read the documentation. Depending on the clock, epoch is defined or not. So for C++20, the epoch of system clock is unspecified before, and then it's specified. But what if, let's say, you're writing a library and you distribute that to people and they compile it, then you don't control which version of the C++ library they're using. So you could maybe do some sort of define and prevent them from doing anything they want. So in that case, well, yeah, it's just you have to read the documentation. Basically, would be so you could say in this case use a C++20 conformal library. I don't think it's great. So it's a bit of a generic advice, but if you're faced with surprising cross-platform behavior, sometimes you can really read the spec in details, like if you have an assumption about something. Okay, I have one coming up. Tricky. Here the problem is it seems like so multiple thread updating the counters, and it seems there's a bottleneck.
False sharing?
No, I have a line.
False sharing.
No, I have this.
But that's for the strap.
Yeah. So I explain what false sharing is. Basically, in simplified terms, your CPU is going to lock your cache line. So if you have 2 bits of memory in the same cache line, you only can write one at once. So what I did here, I don't know if it was me or anyone else's, but I aligned my structure to 64. Now what it means is the beginning of a structure is aligned to 64 bytes. It's not every member. So you're like, no, I did my homework, I thought about it. And no, you did not. So false sharing, fortunately in C++20, there is a standard way to do it without padding. I'll show you the code that is correct. So terse, so compact, but that's correct. One caveat, if for whatever reason you need a cross-platform, your structure to have the same representation in memory. Let's say, for example, you store the structure by dumping it to disk, and you need to be able to reload it. So here you don't want to do hardware destructive interference. You want to do a fixed size, which is going to be the max possible cache size you support. But if you want all your variables to be independent, you do that. Obviously, this is going to increase the size of your structure. So you have to think about it if it's important. No questions so far?
Why don't you use just two objects of one struct?
Two different structures?
Two different objects of one struct which has just one field.
Maybe sometimes you do, but what if they're in the same, let's say you put them in a stack and they're on the same cache line?
No, I mean, like the previous code
Oh yeah.
with a line 64, and this is struct with one field. Imagine that it's just struct with one field.
Oh yeah,
And
you
then
can
you
do
just
that.
have two objects of one struct.
Yeah, of course, in this
I
case.
mean, you probably need to wrap atomic interface though.
Yeah. So yeah, you can do that too. It depends on, that's absolutely valid. You can have two different structures and each are aligned on memory and then you update the structures. Depends on what you're doing. Yeah, sure.
So, this topic actually came up in the last session where we attended today.
Okay.
And the presenter mentioned that the hardware interference, that thing, that doesn't work on Mac.
Oh, okay.
For Mac, yeah. So they said that okay, you have to hard code it for Mac.
What does it do instead?
No,
It's not implemented in
They're
Apple
not
Clang.
supported for Apple Clang.
Doesn't compile.
Oh.
Because hardware destructive interface is not there.
If it doesn't compile, that's great. I'm fine. I can live with that. What I hate is it compiles and then it doesn't work.
Zero.
It's like, yeah. Or everything that doesn't compile is like, I'm good with it. And then you just, okay. That's kind of, so you have to, does it propose to solve it? It just hard code the values?
Exactly. And what he did was that he searched over the internet and found that it's 128.
All right.
But he found that actually it's with 64 it started working.
Okay. Okay, well, that's good to know. So if you didn't hear that, as on Mac, this is not supported yet. Good to know. Okay, so this one is multiple things are wrong with this. But it's pretty frequent that you have a factory, used as a share pointer. So here, there's multiple things wrong with it.
Like, why do you need an empty shared pointer at all?
Yeah, exactly. Why are you using a share pointer? That would be the first question. But
No,
let's.
I mean, why it's empty? You don't construct anything.
Yeah, so assume I'm creating something. That's a typo.
I think that probably the main issue is that I think after that we'll probably use that ACE to do some stuff, and that is not synchronized.
So actually, as far as I know, the compiler is going to create the mutex around here properly.
No, that is correct. But
Yeah.
I'm saying that the problem may be that you will finally use that shared pointer itself
Yeah.
and call functions on top of
Yeah.
this. And those functions will never be synchronized.
Yeah, they're not. So there's the first problem is first of all, are you sure the semantics of your object? Second of all, why are you using a share pointer? Like in the first place. And the other problem is you're doing a static here, you have a bottleneck because every time it's going to access it, you're going to have a mutex lock. So let's say, for example, the design of this isn't great. That's maybe the first thing. You could just say, why don't you return a reference to an object that is creating static, for example? Or maybe you use thread local if you don't need to share the context.
But with magic statics, actually your load will be lesser. So it will not be just a mutex. Like they actually have a different, more efficient algorithm, but you're totally correct that you can just do a new and return the start with.
Generally speaking, I always question when you have a share pointer, do you need shared ownership on your object? It's a good question to ask yourself.
So you need to be very careful though when you say it's like compiler creates mutex. Compiler ensures that it's thread safe
Yes,
and nothing else.
yes,
So for some people, when they hear mutex, they might automatically think that's inefficient.
yes. Yeah, mutex is not necessarily inefficient.
As I said,
Yeah.
for some people, they might think
Yeah.
that it might be inefficient. So it's just thread safe somehow. It's magic static.
Yeah, it's magic static, it's thread safe. You don't know how it's implemented. So the control, what I mean is it's not lock free. So potentially you could have contention. And also the share pointer, like we said, is like why do things. One way you can do this, if you want to do it manually, you could do that. If, for example, because the problem is if you have a static object, the problem is sometimes you don't want to let the runtime initialize it for you when you don't have control on when it is. So you may want to have a lazy initialization of the object in the first time, for example, this function is called. So you could use call once. I'm not saying this is the only way to do it, but this is one way to do it. And you're right, by the way, before that's a typo. Of course, I should create an object. You could, but it's also valid, for example, if you can just share a reference to an object and you are okay with the runtime creating it whenever convenient.
In the previous example, isn't the instance variable, like isn't its lifetime the same as the program lifetime? So then like you never actually
Yeah, correct.
release it.
Yeah. That's why the share pointer is completely useless.
Oh, okay.
Sometimes, we do things by reflex, like reflex in programming. You just, I just do share pointer because this is what I'm used to. I think it's better if you want to do dynamic creation to default to unique.
So in this case, why bother with a pointer at all? And just create a static S.
You could, yeah. You could bother if, like I said, you want to have a lazy creation of the object. Mm-hmm. You want to be sure it's going to be created not before you call the function for the first time.
That will happen.
That's what's static.
Yeah, this one here. Yeah, you can. You say static instance.
Unless they are initialized with the constant expression, they're initialized the first time the function is called.
Correct. And what about the performance of that?
It won't be worse than call once.
It would be the same?
Should be.
Should be.
It should be. They're probably not implemented. They probably don't share an implementation, but if anything, I would expect the compiler version to be faster.
So,
if there's any difference, which I would not really expect.
So you're saying here the best is not even trying to do
the
that?
fast path, I'd expect just a single atomic load once initialization is complete.
Yeah, and then only reads and no writes.
Yeah, it's not even actually, if you look at the paper that proposed magic static implementation, that actually even doesn't even go to a muted block or something, actually deals with thread local and stuff. It's an interesting algorithm.
Okay, so you're saying don't try to be smarter than the compiler implementer. They got you covered.
It's possible that this is also implemented in the same manner as magic static.
So to be fair, the way we solved it is we removed that altogether because it's just not great design. But sometimes you have to do what you got to do, and you need to do this thing. So it's good. Okay, good to know. So it's actually a good approach to do. You rely on the magic static and hope that implementation will get better and better.
Yeah, I think please check it out because this is me saying something. Please don't believe me.
No, I will call you and I'll let you. We have performance problem and I will blame on you. Okay. So this one is about inconsistent performance across platforms. It's, yeah, you should reserve, but let's say you forgot to reserve and some platforms are doing not the same as others.
So what did you say, sorry?
So here what happens is, for example, this loop performs much better on some platform than others.
On some times than the others.
Some platforms.
On some platforms than
Yeah.
the others.
It's really not advanced C++. It's very basic.
So is it how much the vector growth is
Yeah.
platform dependent?
Yeah, it's basically up to the STL implementation to use a different growth factor. And so sometimes your growth factor can hide a performance issue. So let's say it's 2. 2 is pretty good, but some implementer can say it's too aggressive, so I want to do 1.3. And so on platform, so you forgot to reserve, or maybe you can't reserve because you don't know how big it's going to be because you're doing some discovery. And it's very annoying because, of course, I'm showing this to you and, oh, of course, you only have this. But in real life, what happens is hidden in layers and layers of code. At some point, you have a loop on a vector, and you're trying to understand why is it still on Linux and not on Windows, for example, or the other way around. And it's because, growth factor.
There's actually a reason not to use to prevent reclaiming the memory for future expansions.
Okay.
So you need to be below the golden ratio, so below 1.6 something.
Oh, okay. So you're saying it's to prevent memory fragmentation?
If you're below the golden ratio, at some point the remap will leave enough room behind where you used to be for the next mapping to fit into.
Okay.
But if you're in 2, that will never happen.
Okay. So, that's interesting.
What's a remap?
The remap is the reallocation of the vector. So if you push back and the vector is full, you need to allocate new memory for the memory and move everything.
Okay.
So you allocate new memory, you move everything, and then you free the old memory.
Okay.
And then you do it again, and then you do it again. And the thing is, if the memory you freed, the history, the entire cumulative memory you freed is never big enough for your next allocation, then you're doomed to always advance with a pointer. And with 2, that's exactly what happens. If you grow by 1.5, if you go by 50%, at some point, the memory you've used in the past is big enough for your next allocation, and you can look back and use that.
Okay.
Yeah. It's assuming, but I can see that.
Are any real implementations still using 1.5? I thought everyone had moved to 2.
So you're trading, so that's one consideration, and the number of growth you do is another. And everybody tunes it differently. But I'm saying what I'm saying is not that 2 is correct or 2 is incorrect. What I'm saying is there are considerations why a lower number is preferable.
Sure. Just with 100 some odd terabytes of virtual memory, does it matter if you never go back?
The heap is not you typically reclaim from physical pages. So you're not consuming virtual memory, you're consuming actual memory.
I don't know, but it's possible on a newer machine it might matter. Like if you're not local, you eventually will go to a different node. I've never run into this person.
And also he said he has 32-bit platforms.
Yeah.
That's fair, yeah.
So that's actually a great conversation because whoever implemented the STL you're using had certain consideration and they might be adverse to what you're currently doing or favorable, which is why it's exactly what I'm saying. You just fit exactly about what the implementer thought about, so it works great. Then another platform, it doesn't work. Or it works, but it's very slow. And reallocations is for us, like in one of the bottleneck we have most of the time is memory relocation. So if we can avoid memory relocation, if we can avoid, if everything we can do to avoid memory relocation is really great. And so we reserve most of the time when we can. So the growth of vector is platform specific. Generally speaking, reserving your vector in advance is better, but sometimes you can't. And what you can do is a container nobody uses, DQ. I think we use it 2-3 times I'm proud to say we use every single STL containers in the code, at least once.
Isn't a DQ like a linked list?
It's a linked list of arrays, yeah.
It is a linked list.
It's not the linked list. It's an array. It's an array with pointers to buffers. Basically, you have segment table, and then you have contiguous segments of it. That's why DAC is random access.
Okay.
With DAC, is there any issue with cache locality? Is that a concern at all?
So that's where you have to benchmark exactly for what you're doing.
So I assume they generally take that into consideration when deciding the block size, but you can't be certain of that.
Do you have control over the blocks?
And also each block should be
Not
big enough.
content with that.
It's something like, I don't want to say anything
The number
stupid.
of these joints is big compared to the size of it.
That's true.
The blocks are usually not really big. It's like a couple of items. And as far as I know, there is no parameter to control the size of the block. That would be cool, like constructs to say. DQ, or I don't know if you are called DQ, or deck, or whatever, is also great because you can do pretty efficient front insert. Efficient. You still, it's not as, so you have to benchmark. For example, sometimes list is doing pretty good. Or vector, even with the growth and the resize, most of the time that's pretty good. And if you don't know exactly, vector is the container we use the most. Like even like if you want to map, like you want a key value, vector of pair, and it's faster to scan a vector than doing lookups most of the time, or computer hash. And even with the resize, even with regrowth, because the processor is so optimized for the case of a vector and everything in the cache and everything is continuous. Other thing to consider when using containers is the size of the, oh yeah, sure.
Finish your thought.
Oh, my thought can wait.
Okay. So another life hack, potential life hack, if you need to only insert in front, not both in front and back, you still might use a vector.
Yes.
For cache locality, but just reverse it and reverse it.
Yeah, you can absolutely, yeah. I don't know if you all heard. You said if you're only pushing in the front, then just say front in the back, and that's it. So you reverse the logic.
One thing to note about deck is that it's probably the standard container whose implementation varies most between standard libraries.
Yes.
Oh, that's actually a pretty good tip.
It's extremely variable,
Yeah.
especially in how the blocks are allocated and reused.
Yeah.
Yep.
And especially the Visual Studio implementation is horrifically bad. As in, if you have any reasonable sized element, the blocks are one element.
Oh yeah, you're right. Because it's something like 10 or I don't.
Yeah, it's bad.
Yeah.
They basically had something. I don't know the exact numbers, but something like 256 bytes.
Yeah.
And they're divided into the elements, or if the element is bigger, just one.
Yeah.
And
Which implementation?
There's a C Visual Studio one.
Yeah, sure.
Most companies I'm aware of that do this level of multi-platform specific optimizations based on specific implementation, just end up implementing their own containers.
Yeah, we did not because we were very lazy. Perks of being French.
But you're working very hard on being lazy.
Yeah, it's actually a great point. Why did we not write our own containers? So two things we do. First of all, we use the Boost containers, especially since they're pretty recent. For example, for all the hash maps, we use the Boost maps now. For vector, no benefit. Like you're not going to invent anything in vectors. And list is kind of the same. I think so. Where we spend time is we researched. For us, one of the most critical containers is the hash map. We use hash map pretty much everywhere. I don't know if for you it's the same. It's really where implementation can make a huge difference. Hash map is also about the hash function. So hash function, we have our own hash functions, and that's a huge impact on performance. Implementation, since the latest Boost 180, I think that's where there was the introduction of the new hash map. We haven't seen anything doing better, and that's what we use. Before that, we use apps. Yeah, sure.
Just want to mention for vector, there are actually quite a few optimizations you can do. Like,
Oh, really?
The most basic one being like if you have a primitive type, use realloc instead of another, malloc and free internally, so that you don't move the data when you don't need
Yeah.
to. There's other ones depending on if the sizes are a power of 2 or whatnot. But
Can you do the realloc hack and just overloading the allocator?
no, because vector calls allocate and then it deallocates the old one.
Okay, so you have to do.
So you make your own implementation.
You can only do realloc if the type does not support it. Right?
It's
So
primitive,
plain old
yeah.
data, essentially. Only if it's a plain old data.
Yeah. But I'm saying like that happens, and so that's an optimization you can do, and it just avoids moving a whole big chunk of memory.
So for vectors, the way we do it is there is almost always a reserve. And so we minimize allocation. So to answer your question is, why don't we re-implement some of our containers? Over time, what happened is the quality of implementation of the containers, so whether in Boost or other libraries, was good enough for our needs. And we managed to go around some of the limitation by using them in a way that is good. And we have the memory allocator we use that kind of gives us a little bit of leeway as well. But you're right, especially in video games. For example, you may want to have an implementation that doesn't throw, or this kind of thing. We did not. We have some custom containers, 1 or 2, and that's pretty much it, as of 2025. Any other questions for Vector or Deck or whatever? So I'm proud to say we have one user forward list somewhere inside our code. So the single linked list. This one is pretty easy. So it just displays things in different orders on different platforms. Yeah.
That's the definition of unordered.
Yeah, exactly. But yeah, exactly. It's in the name. So what do you expect? But it says you can say unordered, but it's not just the hash function, it's also the implementation. Depending on, so I think it's safe to say that an implementation of that is an array of linked list, but you can decide how you insert in your linked list when you have a collision. So you can do different orders, but yeah, it's an order, so you should not assume anything. So there's no ordering guarantees, and the hash function plays a huge role. So what if you need a consistent order, but you want an efficient array? Same hash function, same implementation, but still it's a little bit, you're playing with fire. Consider a sorted container. What about vector? Vector is great if you want to display everything in the same order, although you can use map. Yes, and if you use multi-map, I think you're also good.
What do we use backpack?
Yes, we use it a lot.
Yeah, but that is also unordered, right? No, that's actually ordered.
Yeah, it is ordered.
This question you say we use for this, what are we working on?
Sorry, I didn't hear.
What kind of project are you working on?
That's what I described in the beginning.
Oh, sorry, I was missing 2 minutes.
Guess you will have to watch a rerun. So I arrived late. So we have this big data analytics platform. We handle petabytes of data on disk and potentially terabytes in memory. And we use it to do numerical analysis and to do forecasting. So imagine a mix of a SQL database, an analytic engine, aggregation, and customized for big projects. That's what we do. And so we are like big users of unordered map. Actually, as an aside, we use unordered map, the std implementation, sometimes by default, because it may have more debugging features than the Boost implementation. I'll show you later what we do for enabling the assertions in the implementation. But as of now, our default, and we've done extensive benchmarks for our use case, again, you should, one thing you should not do is like if someone says, oh, this is the best hash mapping implementation in the universe, and you just say, okay, great, I'm going to use that. You should always look at for your specific use case, because maybe, first of all, there is no difference. Like the std implementation is fine. Okay, that's all my puzzles. Then we're going to talk about perfect timing. I haven't even time for questions at the end. Then I'll just show you, okay, how do we handle, like what to say, multiple terabytes of data and memory, big project, crazy customer yelling at you on the phone. Have you tried to reproduce a 1 petabyte of data on your computer? This kind of thing. So one thing I'm a big fan of is the Sherlock Holmes method. Because we had like everything you can imagine, like compiler bugs, bugs in your implementation. And so the method we have, and sometimes it really drives you insane because you have, the heisenbugs, like the minute you hook up the debugger to your program, it starts working. or you try to recompile the program with debug info, it starts working, or you only have it on the obscure platform that doesn't have a good debugger, or this kind of thing. So this is where we always have this kind of mini therapy session with yourself where you say, it's software, there is an explanation, it's not magic, the computer doesn't hate me. Or maybe it does, but. Performance. So performance matters a lot for what we do, and not necessarily in the way you think about it in terms of it needs to be very fast, but more in the sense that if it's not fast, then the users are going to need like much bigger instances. They're going to need like to buy more expensive computers. And it adds up pretty fast when you handle a lot of data. So the approach we use, that's kind of the mini training we do to everyone who joins the company, is like, first of all, what kind of problem are you solving? Is like, I think Sean in his keynote was saying that is like, no, you're probably not discovering a new computer science problem. It's probably a solution that exists for it. So try to see what you're doing. Is it a sorting problem? Is it categorization problem? What kind of problem is? Then find the right algorithm. Then you want to think about, can it be vectorized? Not every algorithm can be vectorized. Can it be multi-threaded? Like, can I do like a divide and conquer algorithm on my data? Do I have time-space trade-off? Like if I allocate more memory, can I do better things? For example, in compression, that happens a lot. Like if you use more memory, you can achieve better compression ratio because maybe you can create temporary structures, put your data in there, and do better things. But then you're using more memory. And then the memory becomes a problem. That's just use std vector. Even if you think it's like, oh, no, you're wrong. Std vector, and when you start to see pain, think about it. Perfect day implementation is really at the end. It's going to maybe be surprising for people who do a lot of C++ and low-level programming. But if you have looked at the algorithm, shows the right data structure, in terms of performance, you should already be there. And then, yeah, maybe there is some implementation optimization you can do. But if you love C++, like we do, there's tendencies like to go there and say, yeah, I'm going to do something pretty cool. Just always go back to this. So C++ 20, so when we started the project was C++ 11, then 14, 17, now we're 20. So because we have Clang, GCC, Visual Studio, sometimes we cannot use the latest and greatest of C++ 20. We have to use the lowest common denominator. But yeah, what we love, using static assertions, we put it everywhere. Constructs, everything. I think it was a talk I've seen. Annotations everywhere, like it's almost like a Christmas tree. Concepts, metaprogramming. So for example, our serialization has some compile time verification because we didn't have, like in the whole history of all the bugs, most of the bugs we had were logic bugs or the bugs like you saw. But we didn't have that many memory leaks. We had some, or buffer overruns, which if you remember, I think it was one presentation saying, oh, C++ is unsafe. C++ 20, if you use all the modern features, you really need to look for it if you want the buffer overruns. It's possible, especially if you start to index out of index access of a vector, that is very easy to do, but you can do that in any language. One thing that is very important is like what I call Byzantine C++, is basically you mix a little bit of everything. So having a little bit of rigor in the team to say, we prefer this kind of design pattern, to avoid like someone who goes all the way virtual and all the classic OOP, which personally we don't like. It's more a matter of taste. It's not necessarily, but especially with error management, like if you want to use exception, or we like personally to use monadic error, like std expected, this kind of thing. But whatever you do, if you want to use error code all over the place. If you want to use exceptions all over the place, because that makes the code very, very hard to debug. And you're playing a nightmare difficulty level, So you really are trying to lower the difficulty. In the future, I think at some point is you compile your program, that's the unit test. It links, integration test. That's it, your software is ready. You don't need to test it anymore. But yeah, static insertions everywhere really helped us catch bugs. And there's a lot of parts in the code, especially everything which is related to serialization, message dispatch. For example, we catch that you're trying to do something that is not supported. You're trying to serialize objects that don't work. We've added verifications to make sure you don't do unaligned memory access, this kind of thing. Any comment, question? So that's defines we use across platforms to enable as many hardening as we can. This we do in debug, and this one in release. We keep that in release. We measured a very small perf impact that we were okay with.
What does it do?
Sorry?
What does that do?
It does some verification of the, a little bit of hardening and validation on the calling of STL functions. So you don't end up with doing invalid access. It's a very small parachute. Don't expect a miracle, but it's a little bit like video games. Sometimes you cannot always debug the problem with like a lot of bugs we can only use release because otherwise in debug it's too slow. So we like to keep that. So Microsoft has pretty good support for this catches a lot of errors in debug. Then tool we use, so sanitizers, yes, Valgrind sometimes. The problem I have with sanitizers is it's a lot of noise to get something. For example, it says, because we do a lot of things with memory education at the low level, it just screams, oh, what are you doing? But no, trust me, bro, it's fine. So I'm not trolling or trying to start a war here, but usually when we have a bug, the first thing we try to do is to reproduce on Windows because we want to use DMF's Microsoft debugger. I don't know if we're the only one to do, but once you've used the conditional breakpoints and all of that, you prefer to be in the comfort. Sometimes you can't debug is specific, for example, to FreeBSD on a 32-bit ARM device that does not exist anymore. Well, that's your life. Decided to... So third-party libraries management. So how do you use third-party library? By default, is it in the STL? Yes, then use that. And don't try to say, oh, but the implementation, no, just use that. And if you can make a case for the implementation to not be good, let's go down the list. Okay, not available, let's look into Boost. That's what we use. Okay, if not available, then should you write your own implementation or should we look for a good third-party library? We try to be, because we try to strike the right balance between never adding anything or ending up with 100 libraries. In C++, as you know, third-party library management is not the best, especially when you're multi-platform like us. And so the way we use it is like, so maybe I'd be interested in your thoughts. We straight up include them in third-party and they compile with everything, with the rest of the project, and everything is statically linked. We use, for example, let's say we're going to use, I don't know, a library for compression, zlib. So we're going to take the CMake, make sure it works with us, make sure all our compiler flags are properly propagated, and it's going to be compiled with the rest and linked statically. So for deployment, it's much easier. We only have one binary to give to the user. And it's also to avoid conflicts. So regarding how is it annoying to recompile the third party all the time, we use Ccache to minimize the cost. So memory allocator, what we do is we try to not allocate as much as we can. Biggest performance impact, but then we want to be consistent across platforms. And you can have leaks that are not leaks, like the allocator not returning memory to the operating system. Can be very annoying, so you get memory fragmentation. For older version of glibc, it doesn't return memory ever unless you call malloc trim. So it's before 222. So what do? We actually use an allocator that is not so much used. We use the Intel TBB allocator. What we did is we fully reverse engineered the allocator to understand exactly how it works. So we know exactly its strength and weakness. For us, it works. gmalloc is considered, or tcmalloc are considered better allocators for certain, but for our use case, we're very happy. Also, we know exactly how it works. And because we know how it buckets memory, then we can even be careful about, for example, I don't know if you know how memory allocator works, but usually there are buckets that pre-allocate. And for example, if you have an object of 16 byte, going to dedicate that bucket. But if you cross the boundary, then suddenly your object is going to actually use 32 bytes of memory. So when you know how the allocator buckets memory, you can optimize your memory usage. And we used to do global overloading of operators, and we run into a number of issues doing that. So what we do is we do something that should not be allowed. We have two allocators. We have the standard allocator that it comes with whatever library we're using. And we use overloading of STL operators for most of the structures, so we can control how memory is allocated. And we added inside the allocator metrics to know, for example, how many allocations we had, how many memory are we using. For example, for the system, it's important to know how much memory I've allocated. Should I start evicting things from memory? Because we manage to offset the memory. So yeah, so this one doesn't work great on Windows as far as I know, so we gave up. In mmalloc, we had too many crash performance issues last time we checked, but that was like maybe 2 years ago.
Question.
Sure.
Are you using for like TBB for something else?
Yes.
For parallelism?
We used to do it for parallelism, then we gave up on that, and we created our own thread pools. But we use the containers a lot.
Okay.
Actually, yeah, we have made over time there. We used less of TBB, but we still use the concurrent hash map because it's great that you can lock the entry and have control over the access.
Yeah, thank you for explaining how TBB works for TBB team member.
Yeah, I didn't know we were a TBB team member.
For the
But,
rest of us.
Yeah, I'm kidding.
Yeah, but no, we still use it a lot. We use concurrent vector as well. We don't. Did we ever use the atomic? No, I don't think so.
We dropped them in new version because C++ now have them.
Yeah, exactly. So there's this interesting thing about the graph. We tried to play that. The thing is, the way it works, so basically the most parallelization we do is we have some sort of internal map reduce for certain aggregations. But since it's pretty predictable, using our own threads and dispatching, like doing the division ourselves, turned out to be more efficient. We also do something that we should not be doing, is we statically link TBB in the allocator inside the code.
Yeah, shouldn't do that. I mean, the allocator, I'm not sure, but TBB is not supposed to be.
Yeah, well, we do it anyway.
That's your fault?
Yeah, it's because because of the scheduler instance. And
Yep.
Yeah. So we have a third-party library that we give to our user.
I want to chat more to understand what was wrong with parallelization use cases. And have you ever tried like parallel algorithms from STL?
Like parallel 4?
Like for each, stood for each with execution policy.
I don't think you can get a lot from our use case because of the predictable nature of what we are doing and the fact that we already had thread pools and we just hooked into it. And basically we have we need to do multi-threading for the networking part already. So we wanted to do thread affinity, this kind of thing. So we divide the work when it arrives to the database already. So that's why we stopped using the TBB scheduler. And we don't use any scheduler for that matter. because we have the way our multi-threading works. We already know in advance what we're going to do. But yeah, sure, happy to talk later. But we like TBB a lot. And yeah, the allocator is pretty good. So how do you do heisenbugs, race conditions, everything? So actually, the fact that we have so many platforms, the undefined behavior we talked about, we have them usually during tests because we have I don't want to say every compiler, but so many of them. We have also a lot of different platforms, different architectures, so you catch them. The low-tech way is we basically have a Python script that runs the test until it crashes. I don't know if we're the only one to do that, but it's actually our best debugging tool. And once you catch it, then you have a debugger hooking up directly to it. And then you just wait. And if it takes like 2 days to run to it, fine. You just let it run. Yeah, so the process we follow, we produce in debug. We use a lot of assertions. Helps find problems in debug that can materialize itself later in release. Clean sanitize helps, valgrind helps, but to be honest, it's really like old school debugging when you have a problem. Compiler bugs. So when it's a compilation error that should not be here, just rewrite. So we run into compiler bugs, I would say once every 6 months, like maybe. So back to the Sherlock Holmes method, sometimes you realize there's nothing wrong with your code and it's actually a compiler bug, but don't ever assume that you're probably the one who made a mistake. Compiler crash, mostly Visual Studio, but we make GCC crash sometimes. And I'm not talking like running out of memory, but sometimes do something a little bit too insane and the compiler hates it. The one we really hate is, so we had this bug pretty recently. We're using GCC 13, I don't remember exactly the same version. And that's actually a very funny story. Moving code from header to CPP, the code was crashing all the time. And we didn't debug what the compiler was doing, but we ended up doing some sort of mem move, which was resulting in unaligned memory access. So remember the bug we had with the ARM. So single instruction, multiple data on Intel also require alignment. For some reason, the compiler was creating code that was not properly aligned. And it just crashed. Code was correct. It's just moving from header to CPP, suddenly the compiler decided to do that. 2-3 days of work.
What do you think about upcoming std.cmd?
Which one? Sorry.
Upcoming std.cmd feature. Have you heard about that?
I haven't looked at it.
Okay.
We will look into it. My thought about vectorization is if you want to make ChatGPT stupid, you just ask ChatGPT to vectorize code. And that's a good hint. It's a difficult problem because usually the vectorization code it offers is complete garbage. So what is std.sim supposed to do?
Basically, I mean, the author of the proposal doesn't like when I'm saying that, but it's abstraction on top of, like abstraction of intrinsic.
So we've used boostsim from Joel Falcu. It works pretty well for certain algorithms, and we still use it. For example, we have compression algorithms that are fully custom and written with vectorization. I don't know how it would help there. But yeah, sure, we'll look into it.
I know from a fact, I know that like you cannot have like a portable SIMD implementation that is efficient at the same time and portable. Because, for example, ARM permutes in ARM and permutes in Intel, they were very different. Like these parts
And you can still have that.
Sorry?
You can still have that.
How?
Your CMD implementation will just distinguish between different instruction sets.
But you will need to have two implementations
Yep.
just with that.
Yep, but that's
okay,
abstraction
fine.
for
Yeah,
like
okay.
we internally, I mean, not we, C++ standard library internally going to have like 2, 5, whatever it's needed, number of implementation, but then it's abstracted for the users. And if they're not satisfied with the performance, that's also fine. They can use intrinsics directly.
Okay. Can you mix those two codes together?
Yep.
Okay.
I mean, at least that's my understanding, but I'm pretty sure you can.
I tried Google's highway library, and they were trying to like abstract that you are like platform ignorant. You don't know the number of lanes in a vector, and you don't know whether it's ARM and Neon, but the performance was not good. Like you write for works fine on x86, it doesn't work well for a ARM or vice versa.
Well, definitely we're going to look into it. Vectorization can give you like 4, 8x, so it's always worth looking at it. So again, it's always kind of same vibes. So you have a blocking issue, reproduce as much of the environment. So here is like, my message is there is no rocket science, there is no mystery method or magic thing. Is like, it's just difficult. It's nightmare difficulty mode. It's just going to be difficult. Performance is, so I think I've done software engineering for, I don't know, 27 years. The older I get, the more I like stupid vector, the most stupid implementation possible first, and then let's see how it goes. Going faster means you're doing less is something that is interesting way to look at performance. That means you need to do less if you want to go faster. You don't mix micro benchmarks and macro benchmarks. And you also make sure, especially if you're like passionate about optimization, you don't spend time optimizing things that are useless. Again, not inventing anything here. Regressions, the same is like we have basically every week we run full-scale automated tests. And when you have a regression, you try to, if like not great week, like you had 10 major commits, where you do binary search and try to find which commit introduced a regression. And if it's really a bad week, it's going to be a little bit at every commit. So debriefing, we'll use the method from the US Air Force, or it's like basically, we don't care who did what. We just try to figure out where the problem is, because you really don't want to have anyone in the team try to hide what they did. And we try to be unemotional about it. It's basically the method we go through every time. Yeah, and if there was only a conclusion, is just accept that you've decided to do C++ and you decided to play a nightmare difficulty level. It's not going to be easy. There's no silver bullet. You know, there is a software management book, that's the name. It's just going to, it's going to be hard. I don't believe, like, it's always fashionable to say, oh, if only we were to make the language easier to avoid the problem. If you're going to do brain surgery, at some point you're going to open someone's skull, and there's no way around it. And that's the message. Questions? No question?
Thank you.
Well, you're welcome. Thank you for coming.